Welcome to Earthly Teachings, where learning is clear and powerful. Today, we are working on Mathematics N6. Let's learn together about finding areas and volumes. By the end of this video, you will be able to, first, understand the concepts of definite integrals for areas and volumes, and second, use a step-by-step method to sketch various types of graphs, which is a critical skill for these calculations. Let's begin. First, let's refresh our memory on the foundations. You're likely familiar with calculating the area bounded by curves using the definite integral from your N4 and N5 studies. The definite integral is a powerful tool. It allows us to find the exact area between curves. But what is it actually doing? The concept is quite clever. The bounded area is divided into a very large number of extremely thin strips. We can choose either vertical or horizontal strips. The area of each strip is an approximation. If we add up the areas of all these strips, we get a good estimate of the total area. This process of adding things together is called summation. The answer becomes more and more accurate as the number of strips approaches infinity, meaning they become infinitely thin. The definite integral is the mathematical tool that performs this summation for us, giving the exact value. Now we can use a very similar procedure to calculate the volume generated when a two-dimensional area is rotated about an axis. Instead of thin strips of area, we'll be dealing with thin disks or washers of volume, which we then sum up. We'll explore this in more detail in later videos. So the key idea for both areas and volumes is this. We base our calculations on a single representative strip. This representative strip will be either a vertical one, which is perpendicular to the x-axis and parallel to the y-axis, or a horizontal one, perpendicular to the y-axis and parallel to the x-axis. Choosing the right strip can make a calculation much simpler or much harder. For now, it's enough to know the options. The most important thing is that these calculations always start with a sketch of the area or volume. A clear sketch is the foundation for setting up any integration problem correctly. So let's begin by mastering this fundamental skill. Sketching curves. Our objective in this section is to develop efficient strategies for sketching various types of curves. While you could always sketch a curve by creating a table of values and plotting points, that's often a time-consuming method we want to avoid. Our goal is speed and accuracy. Instead, we can use the equation of a curve to quickly identify its type and key features. Here are some general hints that will help you. First, sometimes you can rearrange an equation to make it more familiar. For example, the equation x equals the cube root of y looks a bit unusual, but it's the exact same curve as y equals x cubed, which you probably recognize immediately. Second, finding where two curves intersect is crucial. These intersection points are not just part of the sketch, they often define the limits of integration for our area and volume calculations. We'll see this in action later. Third, calculate the x and y intercepts whenever they are easy to find. An intercept is where the curve crosses the x or y axis. Remember to set the other variable to 0 to find them. Fourth, pay close attention to whether the equation has a constant term. Many curves without a constant term, like y equals x or y equals x squared, pass through the origin. However, even a small constant term like the +2 in y equals x plus 2 will shift the entire graph, meaning it will not pass through the origin. Fifth, recognize when you can sketch a curve by transforming a simpler, familiar curve. For instance, you can sketch y equals x squared plus 4 by just taking the standard parabola I equals x squared and shifting it up by 4 units. And finally, sixth, explore symmetry. Some curves are symmetrical about the x or y axis, or even the origin. Spotting this can cut your work in half. Keep these 6 hints in mind. As we go through different types of graphs, we'll see how to apply them. Let's begin our review of algebraic and trigonometric graphs, starting with one of the most fundamental types. Straight lines are the easiest to sketch. The general equation for a straight line is y equals mx plus c. Here a c, m represents the slope or gradient of the line. A positive m means the line goes up from left to right, while a negative m means it goes down. The c value is the y-intercept, which is where the line crosses the y-axis. To draw a straight line, you only need 2 points. The easiest points to find are the intercepts. To find the y-intercept, set x equals 0. To find the x-intercept, set y equals 0. Then, simply connect the 2 points with a straight line. If both intercepts are at the origin, you'll need to find one additional point, for example, by setting x off by 1. A useful reminder, the equation of the y-axis is x equals 0, and the equation of the x-axis is y equals 0. Next, let's look at a type of graph that you'll encounter very frequently. Parabolas are defined by quadratic equations. A parabola can be in one of two general forms. Either y equals ax squared plus bx plus e, which gives you a vertical parabola, or x equals ay squared plus by plus c, which gives you a horizontal parabola. The coefficient a tells us two things: the direction the parabola opens and its width. For the form y equals ax squared plus bx plus c, if a is positive, the parabola opens upwards. If a is negative, it opens downwards. This is an essential visual check to make as soon as you see a quadratic equation. For the horizontal form, x equals ay squared plus by plus c, the rule is similar. If a is positive, the parabola opens to the right, and if a is negative, it opens to the left. Parabolas are always symmetrical. If b equals 0 in the vertical form, y equals ax squared plus c, it's symmetrical about the y-axis. If b equals 0 in the horizontal form, it's symmetrical about the x-axis. To sketch a parabola, you need to find a few key points. Calculate the intercepts as before. For a parabola that opens upwards or downwards, you also need to find the vertex, or turning point. Its x-coordinate is found with the formula x equals negative b over 2a. For a parabola that opens to the right or left, the y-coordinate of the vertex is found with the formula y equals negative b over 2a. Let's move on to hyperbolas. These are another common type of graph with a distinct shape. Hyperbolas come in two main families. The first is the reciprocal function family, with the general equation y equals c over x, or equivalently xy equals c. The constant c determines the location of the graph's branches. If c is positive, the branches of the hyperbola will be in the first and third quadrants. If c is negative, they will be in the second and fourth quadrants. The x and y axes are asymptotes, meaning the graph approaches them but never touches. The second family of hyperbolas is defined by this equation involving the difference of squared terms. For example, x squared over a squared minus y squared over b squared equals 1. For this form, if the x squared term is positive, the hyperbola opens left and right. Its x-intercepts are at negative a and a. There are no y-intercepts. If the y squared term is positive instead, the hyperbola opens upwards and downwards. Its y-intercepts are at negative b and b, and there are no x-intercepts. Let's now consider circles and semicircles. The equation of a circle is a classic example of a quadratic relation. The general equation for a circle centered at the origin with a radius of r is x squared plus y squared equals r squared. This equation defines the entire circle. However, sometimes we only need a part of the circle. We can express this using semicircles. To get the semicircle above the x-axis, we solve the equation for y and only take the positive square root. To get the semicircle below the x-axis, we solve for y and take the negative square root, because in the bottom half of the circle, the y values are negative. In the same way, we can define semicircles that open to the side. Taking the positive square root when solving for x gives us the semicircle to the right of the y-axis, where x is positive. And taking the negative square root gives us the semicircle to the left of the y-axis, where x is negative. This ability to isolate specific parts of a circle will be essential when we set up volume integrals by rotation. Next on our list are ellipses. An ellipse can be thought of as a stretched or squashed circle. Its general equation is x squared over a squared plus y squared over b squared equals 1. The constants a and b define the intercepts and shape. The x-intercepts are at negative a, and the y-intercepts are at negative b and b. If a is greater than b, the ellipse is horizontally elongated or wider than it is tall. If b is greater than a, it is vertically elongated or taller than it is wide. Here's an important point to remember. The defining feature of an ellipse's equation is the plus sign between the two square terms. If this sign were a minus, it wouldn't be an ellipse at all. It would be a hyperbola. And what happens if a and b are equal? Well, if you set a and b to the same value, say r, the equation becomes x squared over r squared plus y squared over r squared equals 1, which simplifies to x squared plus y squared equals r squared. This is the equation of a circle. So, a circle is just a special case of an ellipse where the two axes are the same length. Let's now turn our attention to transcendental functions, starting with exponentials. Exponential functions are crucial in many fields, from finance to physics. A common form you'll encounter is y equals a times e to the power of kx. Here, e is Euler's number, an important mathematical constant. Let's look at the key features to sketch this. First, the y-intercept. When x is 0, e to the power of 0 is 1. So y equals a times 1, which means the y-intercept is a. Next, the x-intercept. Can e to the power of kx ever be 0? No, it's always positive. So if a is a positive number, y can never be 0. Exponential functions of this form typically do not have an x-intercept. So what does the graph look like? The value of k determines whether the function is increasing or decreasing. If k is positive and a is positive, the function grows rapidly. It's an increasing function. If k is negative and a is positive, the function decays. It starts high and approaches the x-axis. It's a decreasing function. In both cases, for this form of exponential function, the x-axis acts as a horizontal asymptote. The curve gets closer and closer to it, but never actually touches. Closely related to exponentials are logarithmic functions. In fact, a logarithm is simply the inverse of an exponential function. We'll focus on the natural logarithm, written as ln, with a common form y equals a times ln of bx. Remember the fundamental relationship between logarithms and exponentials. The statement y equals ln of x is identical to the statement e to the power of y equals x. This is the key to solving for intercepts. Let's find the y-intercept by setting x equals 0. But you cannot take the logarithm of 0. It's undefined. So these logarithmic functions have no y-intercept. Now for the x-intercept, we set y equals 0. This gives us 0 equals a times ln of bx. Dividing by a, we get 0 equals ln of bx. Using our key relationship, this is the same as e to the power of 0 equals bx. Since any number to the power of 0 is 1, we have 1 equals bx, which solves to x equals 1 over b. This is a very useful formula to remember for the x-intercept. The graph starts near the negative y-axis and crosses the x-axis at this calculated intercept. It has a vertical asymptote at x equals 0, the y-axis, getting closer but never touching it. We've covered up to quadratics, which give us parabolas. Now, let's explore cubic functions. Cubic functions are polynomials of degree 3. Their general form is y equals ax cubed plus bx squared plus cx plus d. The basic shape depends on the leading coefficient a. If a is positive, the graph generally increases as you move from left to right. It starts low, goes up, possibly has a turning point, and then continues up. If a is negative, the graph generally decreases from left to right. It starts high, goes down, possibly has a turning point, and then continues down. A special case is y equals ax cubed. This simple cubic has a point of inflection at the origin, meaning it flattens out before continuing in the same direction. The shape again depends on a. Just as a reminder, a similar pattern applies to the cubic function x equals ay cubed. Its shape is the horizontal reflection of the y form, with a determining if it generally goes right or left. To get a more precise sketch, you would need to calculate the intercepts and the turning points. We find turning points by taking the derivative of the function, setting it to 0 and solving for x. But for a general sketch, knowing the leading coefficient a gives you the fundamental shape. Finally, let's briefly review trigonometric functions, as these can also be used to define boundaries for area and volume problems. Trigonometric functions are periodic, meaning their graphs repeat in cycles. We can draw other graphs of these trigonometric functions by making the necessary changes to the basic graphs. Let's look at sine. Here we see 3 variations on the sine curve over the interval from 0 to 2 pi. We have y equals sine x, y equals 2 sine x, and y equals sine 2x. Notice the effect of the coefficients. Let's start with y equals sine x, shown by the solid line. The coefficient of 2 in y equals 2 sine x, shown by the top-dashed curve, increases the amplitude. It stretches the graph vertically, so it oscillates between -2 and +2, instead of -1 and +1. Now look at the coefficient of 2 inside the sine function, in y equals sine 2x, the bottom dashed curve. This changes the period. It compresses the graph horizontally. The curve now completes 2 full cycles in the same space that the original sine x completed 1. Understanding these transformations, amplitude and period changes, allows you to sketch any basic trigonometric function without needing to plot dozens of points. Now that we've reviewed the types of curves, let's put it into practice. This table, titled Example 5.1, provides a series of equations and asks us to identify the type of curve and any key information for sketching. This is an excellent exercise to consolidate our understanding. Let's start with the first equation, y equals 2x. Since x is to the first degree, we know this is a straight line. Because there's no constant c, we know it passes through the origin. To sketch it, we need another point. We can find one by setting x equal to 1, which gives y equals 2. So our second point is 1, 2. The next equation is y equals 2 over x. This is a reciprocal function. Its general form is y equals c over x. Comparing, we see that our constant c is 2, which is positive. This tells us it's a hyperbola in the first and third quadrants. Now, let's look at y equals x over 2. We can rewrite this as y equals 1/2 times x. Again, this is a straight line, but this time the slope m is 1/2 and the y-intercept c is 0. So it's a straight line through the origin with a smaller positive slope. Our next equation is y equals 2. This is a special type of straight line. Since the value of y is always 2, regardless of x, it's a horizontal line. It passes through the y-axis at the point 0, 2, and is parallel to the x-axis. Similarly, x equals -1 is also a special straight line. This time, the x value is always negative, shout to 1, so it's a vertical line. It passes through the x-axis at -1 and is parallel to the y-axis. Let's analyze y equals 2x plus 3. It's a straight line. The y-intercept c is 3. To find the x-intercept, we set y to 0. So 0 equals 2x plus 3, which means -2x equals 3, and x equals -3 over 2. The intercepts are at 0, 3, and h3, 2, 0. Let's continue with more examples, focusing now on parabolas. First up is y equals x squared. This is a parabola. The coefficient of x squared is 1, which is positive, so it opens upwards. There's no bx term or c term, so its turning point is at the origin, 0, 0. It's a classic example, symmetrical about the y-axis. Next, y equals 4 minus x squared. We can rewrite this as y equals -x squared plus 4. The coefficient of x squared is -1, so it opens downwards. The c term is 4, so the y-intercept is at 4. To find the x-intercepts, we set y to 0. 0 equals 4 minus x squared, which gives x squared equals 4, so x equals plus or minus 2. This parabola opens downwards from a turning point at 0, 4, and crosses the x-axis at a 2 and 2. Now consider e equals 4 plus x squared. This is the same as y equals x squared plus 4. The coefficient of x squared is positive, so it opens upwards. The turning point is at 0, 4. If we try to find the x-intercepts by setting y to 0, we get 0 equals x squared plus 4, so x squared equals -4. This has no real solution. So, this parabola has no x-intercepts. It starts above the x-axis and opens upwards. Let's change focus to x equals y squared. This is a parabola of the form x equals ay squared. The coefficient of y squared is 1, which is positive, so it opens to the right. The turning point is at the origin, 0, 0, and it's symmetrical about the x-axis. Finally, for this set, x equals 9 minus y squared. Rewritten, this is x equals negative y squared plus 9. The coefficient of y squared is negative, so it opens to the left. The x-intercept is at 9, 0. The y-intercepts are at plus or minus 3. Let's tackle a few more complex-looking equations. Remember, the first step is often to rearrange them into a more recognizable form. Our first equation is y equals the square root of x. Whenever you see a square root, a great strategy is to square both sides. This gives us y squared equals x. We now recognize x equals y squared as a parabola that opens to the right with its turning point at the origin. But here's the crucial detail. Our original equation was y equals the positive square root of x. This means that y cannot be negative. Therefore, we must only consider the top half of the parabola x equals y squared, the part where the y values are positive or 0. This gives us a single upward curving arc starting at the origin. Let's analyze x squared equals 4 plus y squared. This doesn't look like our standard forms. Let's rearrange it. If we subtract y squared from both sides, we get x squared minus y squared equals 4. Now, if we divide everything by 4, we get x squared over 4 minus y squared over 4 equals 1. Look at this equation. Do you recognize it? It's a hyperbola of the second type. The x squared term is positive, so it opens left and right. The x-intercepts are at the square root of 4, which is plus or minus 2. And as expected for this type of hyperbola, there are no y-intercepts. Next, x squared equals 4 minus y squared. Let's rearrange this. Adding y squared to both sides gives us x squared plus y squared equals 4. This is the equation of a circle. The center is at the origin, and the radius is the square root of 4, which is 2. Finally, let's look at y equals the square root of x plus 1. Again, we square both sides to get y squared equals x plus 1. This is a parabola opening to the right. Its turning point is at minus 1, 0. But just like before, the original square root was positive, so we must take only the top half of this parabola. Let's quickly recap what we've learned today. We started with the fundamental concepts of finding areas and volumes using definite integrals and the representative strip method. We then saw that a crucial first step for any integration problem is to sketch the region involved. We developed a strategy for sketching curves, focusing on identifying the type of curve from its equation and using key features like intercepts, turning points, symmetry, and asymptotes, rather than tedious point plotting. Finally, we applied this strategy to a series of examples, practicing how to deduce the shape and features of straight lines, parabolas, hyperbolas, circles, and semicircles directly from their algebraic equations. This skill is the cornerstone of the work we will be doing in this module. Take the time to practice identifying and sketching these curves until it becomes second nature. Understanding the boundaries of your region is the first and most important step to solving area and volume problems. Thank you for watching. Like, subscribe, and continue learning with Earthly Teachings. See you next time.